Welcome to 9 Plus, a podcast in which we talk about some of the research work being carried out by staff at Waterford Institute of Technology. My name is Rob O'Connor. In this episode, I'm speaking with Ramesh Raghavendra and Eoghan O'Donoghue of the SEAM Group, that's SEAM, Southeastern Applied Materials. It's an applied research group that is concerned with advanced manufacturing, material science and engineering. In layperson's terms, how to make stuff out of stuff. They're also both founding members of 3D Wit, which specialises in the hugely exciting area of 3D printing. And recently, Ramesh was the winner of the Research Impact Award at WIT, recognising the positive collaborations Ramesh and the team have fostered with industry. During the conversation, we talked about non-destructive analysis, simulation, and I learned a new term, additive manufacturing. If you're not familiar with it, hopefully you will be a little wiser after listening to this podcast. As always, I began the chat by asking Ramesh and Eoghan to state who they are and what their role is at WIT.
I'm Ramesh Raghavendra. I'm a director of the SEAM Research Center. And I'm also a founder of 3D Wit, which is a spin-off center of SEAM.
And Eoghan?
I'm the operations manager at SEAM. I'm responsible for all the day-to-day running and the organised chaos that is our day-to-day lives over at SEAM.
Okay, organised chaos. Okay, I like the way you're thinking. Right, can we start by just describing what is SEAM? Okay. So, Ramesh.
Okay, SEAM is an industry-focused applied materials research center providing materials engineering solutions for wide-ranging industrial sectors, from medical devices to precision engineering to pharmaceuticals to food, electronics, constructions, and so forth. Yeah. In fact, we have several niche technologies, such as number one is we are the CT scan experts in Ireland. So CT scanning is a computer tomography technique, which we use for providing non-destructive investigations and also for product design optimizations and metrology. So we use the CT technology for all these applications. And the second area of our expertise is in the area of simulation and modeling. Yeah. So, for example, modeling of manufacturing processes or complex systems, which using these kind of techniques, right, it reduces the need for building up prototypes, right? So we use these modeling and simulation techniques, to avoid the costly prototyping techniques. Yeah.
Okay, so can I ask you the dumb immediate question?
Yeah.
So when you talk about materials, you're talking about manufacturing using specific elements or compounds that might have certain properties. Is it like, so for example, semiconductors that conduct electricity or don't conduct electricity, or maybe have a certain threshold for heat or whatever it might be, rather than just building something out of bricks?
No, okay. When I talk about material, right, when we talk about material, it is wide-ranging material. Whether it is polymers, it can be plastics, it can be metals, it can be ceramics. Anything, any materials, it does irrespective of whether it is.
We have a very broad reach in our expertise. We have a wide range of different engineers from different backgrounds who've worked in all types of different industries, and also from strongly research backgrounds and things like that. But also, we've always been investing in our equipment resources. So we have the tools to solve any different type of problem that comes from industry. And that can be anything from something broke and people don't know why, but also, there's this weird stain on my product, or there's foreign material in it and my customer isn't very happy that there's black granules in his cup of tea.
So can I ask you then to give me an example? So you mentioned CT scans.
Yeah.
Okay. So what are the material constraints with respect to CT scans?
Well, when we started off, we had a 180 kV system. That's the power, for example. That gives a rough idea the size of object you can look at.
That's kilovolt, is it? Or?
Yes.
Yeah, okay, right, yeah.
Okay. So a CT is much like medical CT. It allows us to create a three-dimensional virtual model of an object. And then we can go and virtually chop into it, look inside in it, check if the size of it is right, or if we have two parts, make sure they go fit together right, or maybe something's warped or something like that. Now, when we start out with that system, you'd look at something maybe the size of your fist. Okay, so as time went on, we had the opportunity to get funding to buy a bigger system, and that was up to 300 kV. And now we're up to the kind of place where you could put something the size of a washing machine into it. So we can look at a much larger object. Okay. Now there are limitations depending on the material composition. So if we have something like a big chunk of lead, firing X-rays through it isn't going to be very effective. So that would be a small thing. But if we were looking at something like a large carbon reinforced structure, like a wind turbine or something like that for power generation, we could look at quite a large object then because it's not as dense. And those would be the kind of limitations that we'd work with in that kind of technology.
So, materials science. Ramesh, what discipline or disciplines would this fall under?
Again, since as I said to you in the beginning, right, we are providing service or our center, right, it looks after wide-ranging industrial sectors, right. So primarily we deal with a mechanical engineering, or if you're looking mechanical or biomaterials or materials engineering.
Yeah.
But we can also work on civil engineering as well, because we assist construction industries or construction companies and so forth, right? So it's a wide-ranging sectors, and even the electronics as well, yeah.
I suppose to put it another way, everything is made of something.
Yeah.
Yeah.
Okay, and that falls under our remit. And that even goes into things like that you wouldn't expect, like the food sector, for example. Like cheese is a material. Right, that's a better way of putting it.
Okay.
And in the past, we've characterised the holes in Edam cheese and things like that to make sure that they fell within the constraints supplied by the European Union, for example.
Are you telling me there's actually
a specification for the size of holes in cheese?
Yeah.
Okay.
Yeah.
We've put in all kinds of random things into the CT, which increases our skills and broadens the number of things that we can help industry with. But you can have a bit of fun with it every now and then as well.
In fact, just to give you an example, right, we did product for in relation to this cheese, right? We got a big chunk of cheese, big block of cheese, right? We did a CT scan, yeah. And then that CT scan, after doing the CT scan, the product went all the way to Brussels, yeah. And then it came back, and then we did again another CT scan on the same cheese block, yeah. Just to see how the transportation impacts the voids inside, right? The collapsing, how much it collapses, or the variations, right?
Well,
just to give you an example of that, right?
We're still waiting for the crackers to turn up, though.
Okay. Yeah, what did you do with the cheese afterwards?
Oh, no. Unfortunately, nobody dared to eat it.
So the idea there is, you're assisting companies and possibly researchers with compliance, but also to ensure that what's going on inside the things that they make are actually what they think is going on.
That's
is that correct?
Absolutely, yeah. And to take a step back, I suppose, we're part of the Gateway programme that's funded by Enterprise Ireland, okay? And this is a range of research centres that are set up across Ireland in different areas of speciality. And the concept behind them is that a lot of companies don't have the money to buy an expensive piece of equipment that might solve one problem every 6 months. And then they don't maybe have the money to pay for the expert to be able to interpret the data and to run that machine. Okay, so philosophy behind the Gateway Centres and SEAM is that we would have that equipment on site, and someone would come to us and say, we have this problem, okay, and we'd say, we have this piece of equipment here and we have the expert here to run it, and you only pay for those 2 days of work that it takes to resolve your problem. So this provides an edge to Irish industry, okay, allows them to access those pieces of equipment, that expertise, and find the answers to problems that may not be everyday problems, but they can be big problems when they turn up. And that's the idea behind the system.
So let's talk about where SEAM, Southeastern Applied Materials, where it's come from. So how long have you been going, Ramesh?
Okay, I'll tell you, right. SEAM was launched as Enterprise Ireland funded Applied Research Enhancement Center, right, in 2009, yeah. Okay, and then we became a Technology Gateway Center in 2012, yeah. But now we are 10 years in Technology Gateway Center, but over the last 5-6 years, we have become the leading Technology Gateway Center in the country, right? And apart from Technology Gateway Center, because the Technology Gateway Center is primarily assisting the industry part of it, right? But we are much more than a Technology Gateway Center now. We have grown into a full-fledged applied research center because we have postgraduates and PhDs working on this thing. So we have grown from an applied research center to a technology gateway center to a full-fledged applied research center.
Yeah. And we support PhDs and training for master's students
Masters.
and all levels as well, where research is the key.
Yeah. So you would be writing papers, publishing papers.
Yes, that's correct.
Publishing white papers and et cetera, et cetera, et cetera. And Ramesh, didn't you win an award recently?
Yes, actually, recently I won this research impact award. Yeah, the first time it has been constituted in WIT under that category. Yeah.
Yeah. So would this come back to the idea? What you're describing to me sounds very applied. It's very much geared towards
It is applied.
real world solutions.
Yeah, the real world is the right term to use there, okay? We don't work a lot in blue sky hypotheticals. We work on real problems and real benefit and value to industry, okay? And that can be the solution to a day-to-day problem, as I described earlier, but that might be the development of a new product, okay, that could give them the edge in the marketplace, or to deal with maybe some kind of consistent problem that's been there with a product that was holding a company back.
Yeah.
Okay, so we do a lot of basically the real bread and butter problems for industry. That would be our day-to-day business, as well as research.
So let's say a hypothetical example. I want to build a smart bike of some kind, right? And I'm a software person, so I'm going to build some sort of Internet of Things capabilities into it, and it's going to connect up to the internet and do something, right? Whatever that might be. But one of the aspects of the bike that I'm interested in, and one of my design goals, is that it is lightweight but durable. And I know nothing about bikes, and I want it to be a more lightweight and more durable bike than regular bikes. I come to you. Would that be how it would go?
Absolutely. That is a kind of things what we do. Right? So first of all, right, if you want to reduce the weight of the bike, right, the first thing we look at it, what is the present material which is being used, right? So we will see whether we can change to a lighter material, yeah. And the second thing is about the design part of it, right? Can we change the design? Yeah. And so we have various techniques to do that. Yeah. One is a finite element analysis. The technique part of it.
Finite element analysis is one of those big lumps of jargon that we try to avoid. Basically, some people refer to it as stress analysis or computer simulation. And basically, it's a computer software technique that allows us to simulate, say, a metal bar, and we can look at what load will this bar take before it starts to bend. Well, we can use the same technique to look at the entire bike and see how it performs with different people on it, or if it's going to bend or break under normal loading conditions, or, is the front wheel going to buckle if you hit a bump in the road or something like that. But also we have other techniques called computational fluid dynamics, another big lump of jargon there, but that's to look at airflow, the mixing of air streams or liquid or anything like that. And in this case, you could look at, the aerodynamic qualities of your bike design and see if it could be a little bit of an edge gotten in there so that people would get a bit further without working quite so hard. Okay. And this also, another service we would look at is maybe the 3D printing of certain components.
Yeah. I mean, once the design has been optimized, using this finite element analysis, which Eoghan has pointed out, then we can also manufacture that part, the optimized part, using a 3D printing, So the 3D printing, right, is apart from printing that, right, you can also reduce the weight using 3D printing because you can build
we have the capability of printing in things like aluminium alloys, but also titanium.
Okay.
Yes. Yeah.
Titanium is a good example of a metal for 3D printing because it's quite hard to work with, to machine or do things with, to make stuff out of it normally. But when you 3D print it, you can build it from the ground up and get whatever geometry you want. And it's a super lightweight material and super strong. So if you want to end up with a reduced weight bike, it would be a key material to look at.
Yeah.
Okay, so let's talk about 3D printing because it's a fascinating area and I know very little about it, right? Yeah. So let's assume, and it won't take much, you can assume that I know nothing about 3D printing. 3D printing is not printing paper, is that correct?
No, that's not correct.
Yes.
So what is 3D printing, right? If you take any conventional part, right, if you want to make a product, right, what you do is you take a chunk of material, you machine, and then you end up your product. As a result, right, since you're machining, right, there's a lot of wastages, Whereas in 3D printing, you start from the raw powder, which is a powder, right? So you build layer by layer by layer, Okay. And as you build the layer, right, the laser will melt apart, and then you build up the product bottom up part, and you end up the product with very little wastages, with less than 2% or 3% wastages.
And this kind of is a key in design, and this is part of the whole 3D Wit and the spin-out company that we generated to educate people in the design requirements for the 3D printing, or what we would call additive manufacturing technique. And this is to move away from most people design nowadays for subtractive methods, which is what Ramesh was mentioning there, where you take a block of metal and you remove just what you need to get the functional part at the end. Okay, but that means there's probably a lot of extra material in there that isn't really doing anything. It's a big lump. Okay, so when you design for additive manufacturing, you just put in metal where it's required. And you can end up with a much more practical, lightweight, elegant structure as compared to conventional manufacturing techniques.
That is why the 3D printing is called additive, because you keep on add powder, right? Whereas the conventional techniques, it is called subtractive manufacturing, because you machine, you remove material. Whereas in the 3D printing, you add material.
So you talk about the powder. So again, I know nothing about this. So I have seen 3D printers at work, and kind of there's a small little kind of arm moving around and doing things. But is the idea that it's dropping this powder?
Well,
how does it work?
In metal additive manufacturing, and to some degree in the polymer manufacturing, but we'll stick to metal for now because that's kind of Seam's area of speciality here. You put down a layer of very fine powder on a metal plate, and where a laser fires down at it, and where the laser hits, you get solid metal. Okay, basically it fuses that powder into a solid metal. The plate then drops down a little bit. More powder gets placed across the top. Laser fires again exactly where you want, because it's connected to a CAD system where you have the model of the part that you're printing. More solid metal is generated. Plate drops down. Rinse and repeat. Could be 1,000 layers until you end up with your finished part. And then off you go. There's various finishing after that to take it off the plate and to polish it up, whatever. But basically, that is the additive manufacturing process.
So, this is a crude example, but it's just trying to get it right in my head. It's kind of like Lego, in that you have a kind of a baseboard, and then you put some bricks on, and I might put some more bricks over here, fewer bricks here, and I might build
Absolutely. It's a very good analogy, because Lego is a layer-wise manufacturing process. Additive manufacturing is very much a layer-by-layer manufacturing process. Actually, one of the first things we actually printed, funnily enough, was actually a Lego man.
Oh, really?
Yeah, the very first part,
Because we scanned using the X-ray, a little Lego guy, and then we printed him out, because it was a nice way that people could access the technology, because everyone knows about Lego and everyone understands how it works, but then we had this metal little Lego man, which was a nice little mascot for us.
When we first set up the lab, the 3D printing lab in 2014, in fact, we are the first production scale metal printer we had in an academic environment, settings, right, in Ireland, right. Got it, right. So in the first year, right, our researchers, right, and also staff, they were very much interested, and they were using a lot of interesting stuff like a Lego man, and then some this top and what do you call
bottle opener.
Bottle opener, and so many interesting things.
That was just the demo part.
No, that's already the demo part. Just to learn as well. Now think of what you can.
I would always say that every time you print something, you learn something.
Okay.
So
absolutely,
use the machine, print things, because that's how you advance your knowledge and the technology, by trying it out and doing things, because that's where you establish the limits or the capabilities,
How long has 3D printing been around?
Oh,
3D printing,
the concept it's been.
The concept is there for quite some time, nearly, I think 1950s, 60s. In fact, the prototyping, it was called then. It was called a prototyping, the real additive manufacturing, what we know of this thing, came about in 1990s, I think, 1990 or something like that,
Because it does sound like a genuinely revolutionary way of doing things.
Absolutely, it's one of the disruptive technologies,
It's like Star Trek type stuff, really.
Absolutely, yeah.
So, could you give us an example of where 3D printing is changing the way things are made?
So for example, now you see now in the space, now I think 3D printing has got wide-ranging applications, right? Predominantly the medical area is the one which has really adapted the 3D printing, right? So for example, if you want to have your own dental aligners or dentures, right?
Yeah.
You can 3D print bespoke 3D printing of your dentures, right? And then the orthopedic industries now it has really taken on 3D print, right? 3D printing, yeah.
Sorry, just to go back to you're talking about like dentures or teeth. So I have to have that. And let's say in the past I would get dentures, and there's maybe 8 versions that I can choose from.
Yeah.
And I find one of them that fits best.
Yes.
Whereas this one I could do a scan
Completely
of
bespoke,
myself.
yes.
Patient or customer specific implants.
Okay.
That's what we're talking about. And the dental industry is one that's really kind of taken the technique and run with it. It's been using it. It's one of the early adopters on a commercial level of the technology, because you can print dental crowns and dental implants. You can put a lot of them on in a single build, and they're not very high. You know, you can understand the size of a tooth. It's not huge.
Yes.
Okay. So it's possible to print a lot of them at a good price. And in the past, these would have been made by a dentist, a very time-consuming process, or it would have been, you know, an off-the-shelf replacement that maybe wasn't ideally suited to an individual.
Yeah.
Okay. So this allowed quality to increase, because, you know, they're making them out of titanium.
Yeah.
Okay, to go into people's mouths, but also the cost came down a little bit because it's a more efficient manufacturing technique for customer specific implants.
And I'm assuming these things scale as well. The more people who do it, the more it's made, the cheaper it gets, blah, 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 the usual type thing.
Well, I mean, the cost of the machines is quite high, which is also, it's a good reason to come to a place like us if you want to dabble in the technology before you spend the money and make sure it's right for you. But the more people that use it, the more machine usage that happens, the more return on investment. You know, it becomes more economical for people to use it.
So I'm not going to 3D print a car.
You
But what I might 3D print
part
part of a car.
Part of the car. A lot
Okay.
of components of part of the car industry is also now they've adapted the 3D printing, right?
Right.
So a lot of car industries, right? You know that inside parts, right? Not as a full car, right? A lot of components inside the car parts are being made by 3D printing. Yeah.
Another big area would be the aviation industry, because you can have reduced weight components which will have similar strength to, you know, parts that are made conventionally.
Yeah.
And, you know, every little bit of weight saving in a, you know, 787 or an A380 or something like that, it was a fuel cost, okay, or a fuel saving for the company. And that leads to slightly greener technology and everything like that, because you don't need to burn as much fuel to get where you're going. So it's being heavily adopted there to reduce weight.
Yeah.
Thing. And other areas now, coming back to the medical thing, right? The orthopedic areas and all now, it's tremendously now. It's they are now adapted. Next to dentistry, it is the orthopedic industry in the medical sector which has adapted, right?
Oh, I'd imagine.
So
You're talking about titanium hip replacement. It's the first thing that springs to mind.
And one of the other things is that now you can make a porous structures in 3D printing, right? That allows the bone to grow into this thing, right?
Oh, wow.
So bone regrowth, right? So that is another fabulous advantage of this 3D printing technology, yeah.
So let's again. Now I'm not a medical person, but let's just say in a hypothetical situation, I break my arm and it's a bad break of some kind.
Yeah.
Somebody could do a scan of my arm and build a little tiny part. So instead of putting in screws and whatever, you could put this thing in instead.
That's
and
right.
then the bone would heal around.
Bone will grow into that and it will heal, because you can build a kind of a porous
Yeah.
structures and that
Yes.
the bone can grow into that, yeah. And then it becomes a very robust. Then we also make,
Wow.
yeah.
That's amazing. I mean, that
Absolutely.
genuinely is amazing.
That's
yeah.
correct. Again, right, this implant, right, if you're making a titanium, right, then the titanium is going to stay there forever, right? So instead of titanium, right, you can make it with a magnesium, right? Because magnesium has got the properties of bioresorbable. In the sense, what I mean by bioresorbable, right, after some time, it will dissolve, yeah. It
We're
will
wandering into very heavily our research area there. You know, this isn't on the market yet or anything
It's
like that, but
marketing.
it's something that we're working on developing at the moment.
Yeah.
Which is biodegradable metallic implantable materials.
Right.
Okay? So that's the idea where, much like your example of the arm, we can help the bone to regrow. Okay, so you end up with bone again, you know, your own bone.
Yeah.
But over time, the body will break down the metallic implant and it'll disappear. Okay, so there's no need to go back in to go and try and remove that metal afterwards.
Wow.
Okay, so there's no need for a second operation and all the risks that come with it.
Yes.
This is also, I suppose, a key area for this would be things like facial reconstruction.
Yes, of course.
So people who have had horrific injuries to the face, to help them get a bit of normality back.
Yeah.
So for younger patients, right, instead of using titanium, you can go with this kind of magnesium. In fact, we are currently working on a disruptive technology innovation project, right, involving companies and few other academic institutes together, right, where we are looking into this new materials, So where it can dissolve by itself after the bone, after the tissue grows into it, and then you don't need any more the implant. So whereas if you're putting the titanium, it will be there forever.
Yes.
So instead of that, you can use an alternative material.
There's a nice little, just a spin out or spin off comment there. We bought, or through the funding of the project, we got an EOS M280, it's an M100 system, 3D printer. And this was originally designed as a jewelry printer or precious metal printer, so to print gold and platinum and things like that. So we're using it to print magnesium materials now as biomedical implants.
Wow.
Well, hopefully, if it's successful, the project's going well. But we have to get to the end.
What you're talking about and what you're describing, it sounds like very much like high value manufacturing. I mean, it's high end. You're not talking about,
Absolutely.
Exactly. No, it's all high end, right? But having said that, now we can also do some very other interesting part, right?
Yes.
When
I say high value, I don't mean that as a value judgment, but what I mean is that, you get the idea. Yes.
I suppose this is key to success in the technology is the whole picking the right part. Okay, the technology isn't for printing large components, heavy components, or anything like that. When we first started out, we had people coming to us with parts off the back of a JCB and things like that that are very impractical. And we would tell that customer, here's the price, and they'd go away thinking, oh, that's very expensive, that the technology isn't suitable, or there's a problem with the technology. But the real problem is their design, okay, or the part that they selected for the process, okay. So through 3D Wit, we're working to educate people into making that right decision, to pick that right part or right assembly or component where there's a cost win, okay, where they save money or get a better quality component out of the end of it. And that's the key to success in technology, is to the value, to pick the right part that's going to give you a good return.
Yeah. So apart from this high tech, this thing, we can also do a lot of other interesting stuff. Yeah. So just to give you an example on this interesting stuff, that now SEAM celebrated our 10th anniversary in 2019, well before the COVID. I think now, and
in the before times.
Well before times.
BC.
Good times. And we invited our local minister. We want to surprise our local minister, the then the minister John Halligan. Yeah. So we wanted to scan his head and give him a present his head, on the day, So we invited him just a month before the event, and we asked him to come just for a visit, and he visited us, and we made him to sit, and that was a difficult part to make him sit without him moving, so we used a laser scanner to scan his head. And then we printed his head using our polymer printer, and on the day of the event, we presented him. We put him on a pedestal, his head, and we printed and we gave him as a gift. He really loved it. Yeah.
So you printed John Halligan's head. Okay, who would have been Minister for Skills or so?
He was Minister for Research and Innovation at that time. Yeah. Yes, so he was the correct minister for our center.
I was amazed by how well the hair came out.
His hair, absolutely. The detail of his hair, right, protruding out. Yeah. It all printed so well, and he was very happy with that. Yeah.
Can I ask you, what was it made of?
That was there is a PLA.
PLA,
It's a PLA, which is a.
Sorry, what's a PLA?
It's a polylactic. It's a kind of it's a plastic material.
Okay.
It's a resin
it's
material.
polymer,
It's a polymer material. Yeah.
Okay, so it wasn't out of gold.
Oh no.
We don't have a budget like that.
We don't have funding for that.
I'm reading a book at the moment by a Japanese-American physicist called Michio Kaku, and I'm sure I'm pronouncing that incorrectly, and he's kind of postulating about future space travel and all this kind of stuff. And one of the things he talks about is kind of self-replicating machines, and how potential space colonies could be sustainable into future. So if imagine there was something on the moon or Mars or wherever it might be, and a little bit of it breaks, it's not conceivable to just like place an order on Amazon and it'll arrive the next day.
Yeah.
You need to be able to do these things yourself.
In fact, I think 6 years ago, in fact, the space stations, they have 3D printers, these polymer printers there. Right?
In the International Space Station.
Yeah, they've been trialing it up there. Yeah.
It's trialing up there. No? So they have taken some of these polymer printers, and for any small breakage, small parts, they can print there itself. Yeah.
Okay. So wow.
It brings us into the idea that in 10 years, when you buy something from Amazon, you might buy the CAD data, and then print it at home yourself. And there you go. There's the part that you ordered, rather than waiting for DPD to deliver it.
Do you think that we'll get to the stage where 3D printers will become a bit?
Oh, absolutely.
It's going to become common. It's going to be common usage even in everyday's house as well.
Polymer anyway.
Yeah, polymer. Yeah, exactly.
Yeah, maybe not gold.
Yeah, no. Metal is more expensive, whereas polymer printers you can buy for $1,000.
Yeah.
Okay,
But it's nearly there now. I mean, a lot of people are buying them as hobbyists or having them at home for, printing models and engaging in whatever they want to get to know the technology, etc. So
that's why we set up this 3D WIT. Yeah, this 3D WIT it's a spin-off of a SEAM Center where we got funding under Regional Enterprise Development Program of Enterprise Ireland. Yeah, and the 3D WIT is set up to provide primarily to provide training. Yeah. To the industry guys, to the industry operators, and also to our own third level students, and for the school students as well. Yeah. In fact, last year we found partnership with junior cycle teachers, and also IFOM, which is a Science Foundation Ireland Advanced Manufacturing Center. We found partnership with them to provide national training for junior cycle teachers, right? And in 2021, we trained 120 teachers. Yeah. Spanning from North, Midlands, and South. Yeah, wow. 120 teachers. They underwent training. Having said that, now the 3D WIT was supposed to be hands-on training center. Unfortunately, because of the COVID, so we were providing the training with the online, but it was very well received. And there is another 120 teachers have been booked up. So this year in 2022. We are going to start off with another 120 teachers. Yeah.
Wow.
Just to pick up on that whole practical comment, when we set up or conceived the whole 3D WIT idea, it was very much to have it as a practical training, not. And I hope I don't step on anyone's toes here. Not a boring lecture. We didn't want to be standing up at the front of the class. And
I'd be the first to hold my hand up there. You're okay.
So to actually have the equipment that people might use in industry, to have all the different types of 3D printer, all the techniques. We have a carbon fiber printer. We can print in engineering polymers known as PEEK, which are very difficult to work with.
Yeah.
We have a metal printer on site in 3D WIT for training. We have all the software that goes with it. So everything that you might use in the real world in industry can be accessed at one site, and you can have a go, get your hands dirty, and learn the real challenges with using the technology and the real benefits.
In fact, among the academic centers, right, for metal, I think we are one of the leading center in the country, right? We can print magnesium, titanium, stainless steel, maraging steel, nickel-based alloys. We have printed for all these materials for industries. Yeah.
So it sounds to me, right? Again, I don't have an engineering background, but that with 3D printing, there's a huge part of it is a mind shift. Change or a change in imagination, perhaps, as to what can be done.
Absolutely.
And when you talk about, you're talking about junior cycle teachers, you're talking about second level teachers, I assume.
Yes, correct.
So
yes.
It's perhaps about embedding those ideas early in the next generation of engineers and physicists.
In many ways, it's reversing the way people think about making things.
Yeah, when you say additive, so
absolutely. Yeah.
So instead of taking a chunk of material and removing, what you have to get to something, you need to think about building it from the ground up, like a tree grows or something like that. Okay, so I'd often talk about taking a design and stripping it back to its absolute bare bones. It might be just a couple of lines on a sheet. Okay, and then build that up from, we need a certain amount of wall thickness here. We need material here to do this job. We need a connection between here and here to do whatever. Add in just that material. And then you might do simulation and figure out, we need a bit more strength there.
Yeah.
Deal with that. And then you end up with a very minimized, streamlined design for your final component that does everything that, the old-fashioned component did, but is now a completely different thing, but still does the job it's required to do.
So I'm thinking about that quote from Michelangelo about the block of marble, and the statue was always there. I just had to reveal it. This really is the inverse of that.
Absolutely, yes. Yeah.
Wow. Are you getting much kind of, would you say imagination is the biggest barrier that you have with people? I mean, you talk about the JCB guy.
Yeah.
Like, is that,
I don't.
am I being unfair, perhaps?
Yeah, it's a bit harsh.
Yeah.
But I suppose we want to give people, we want to unlock people's imagination.
Yeah.
We want to give them the opportunity to dream and think and conceive new ideas and designs, and then create them into reality. Okay, we want to give them the tools to think in that manner. Okay, so that they can use the technology and get to where they want to go. Okay, so that'd be my way of looking at it.
Yeah, no, it genuinely does sound like a genuinely revolutionary technology. Now I know people say that it sounds like a kind of a hyperbole, but it really does.
Yeah, absolutely. I think in 10 years' time, right? I think this will be a technology where you can see it almost in every household or something like that. And we would like to, and we in Siemens 3D, we would like to promote that to happen. Yeah.
It's always been that idea that if we can get enough people out there in the region that have these skills, and that'll bring in industries that are interested in using those skills.
Yes.
Okay, and hopefully we'll create an additive manufacturing base here in the southeast that'll support job creation, etc. And that's our long-term plan, I suppose.
One last question. So imagine somebody was listening to this and they were thinking about getting into research or starting postgrad or whatever it might be. What advice would you have for them, Ramesh?
Yeah, please come and talk to us, right? As long as they have interest in research, right? Then we can guide them. Yeah. One of the things about this applied research is that now at the end of the research, right, you can feel your work. Yeah, you can see some tangible thing coming out of it. That is thing. As long as they have the interest, because the research, it takes some time. It takes 2 years or 3 years, or depending on what level they want to do research, right? And we have excellent infrastructure. We have excellent facilities, right? All they have to is come and talk to us. Yeah.
Yeah, I think picking something that you're interested in, you're passionate about, because it can be a long road to get a PhD. You might be working on something for 3 years or longer, depending on your situation.
Yeah.
So picking something that you're passionate about, that you're interested in, that you really believe could make a difference in the world or change things, that's a good place to start. Okay, we can provide the tools, but you need to come to us or with the idea, and that's the best way to start things, because you'll be passionate about it, you want to invest your time in it and get it over the finish line.
There's a lot of applications, absolutely. Whether you take over 3D printed electronics is again another area which we are going to get into it in the next year. And so there's a vast application in that, right?
I was just a million ideas going off in my head there about what could be done. To Eoghan O'Donoghue and Ramesh Raghavendra of SEAM, thank you very much for speaking with me today. If somebody wanted to find out more about SEAM, where should they go or how should they do it?
I think we are there in www.seam.ie, SEAM.ie, and we are in Twitter, we are in LinkedIn. There's a lot of opportunities, and we are directly based behind the Allied Irish Bank on the Paddy Browns Road within the industrial estate. And anybody is interested, they can always walk in. They can either make an appointment through this thing, and we are always there to show the facility.
Brilliant. To Ramesh and Eoghan, thank you very much for speaking with me today. We'll be back with a new episode soon. Cheers, lads.
Thank you.
Thanks for listening to this episode of 9plus. You can follow us on Twitter at 9plus podcast. That's digit 9 PLUS podcast. And if you liked what you heard, please leave us a positive review on Apple Podcasts, Spotify, or wherever you're listening. We'll be back with another episode next week.